Hello everyone, I'm Reza Ghoddoosian, the first author of the presented work. In our work, we study instructional videos. Instructional videos can be defined as videos where a sequence of atomic actions take place in order to carry out a top-level task. One can usually associate three main attributes with instructional videos. One, the hierarchical structure between the low-level actions and the top-level task. Second, the contextual dependency between those low-level actions. And third, the high number of action segments that occur in a video with limited background frames. The main problem addressed in this paper is action segmentation. And action segmentation can be defined as the problem of finding action labels and the start and end time of those actions in a video. In the fully supervised version of action segmentation, we have access to action labels as well as the start and end time of them during training. Whereas in weakly supervised action segmentation, which we address in this paper, we only have access to the ordered sequence of action labels at training time. So there's no access, there's no information at training time regarding the start and end timestamps of those actions, and we have to learn that. In order to solve the action segmentation problem, we break down the whole problem into two different subproblems and define a top-down paradigm to solve the problem. The first stage is task classification. In the task classification stage, we receive the video as input and predict the task, top-level task, and the predicted task will be given as input to the segmentation module to do finer action segmentation. Now the input for task classification is the sequence of action labels, as mentioned before, and each action can be decomposed into the verb and object components. We collected these verbs and objects and put them in a set and called the set the video attribute set for that video as input. The video attribute set, along with the task label, will be the inputs. Based upon those, we created this network in order to classify the task of a given video. The two-stream hierarchical task classification network consists of two different streams. The top-level stream, we exploit the semantic hierarchy of a network, where a mapping function is learned to map the video into an attribute space. In order to train this mapping function, we use the attribute labels provided at training time. A second mapping function is also trained to map the attribute score to the task score using the TF-IDF technique widely used in documentation classification. There's also a temporal hierarchy stream at the bottom, where we divide the video temporally into case stages, and a classifier, a task classifier, is trained separately for each stage. And then we combine the results of all these different stages to predict what the final task in the video is. Our experiments showed that different stages have different importance depending on what the task is. As an example, while making chocolate milk, we realized the last stage is the most important stage for predicting chocolate milk, whereas in making coffee, the first couple of stages were the most discriminative stages for predicting if that video is making coffee or not. That's why we trained stage-wise classifiers with different parameters in the temporal hierarchy stream. Now that we've predicted what the task label is, now we formulate our action segmentation problem given the predicted task. We maximize the posterior probability of action labels and their duration and integrate the task probability term where it's 1 for the predicted task and 0 otherwise. The benefit of that formulation is that we constrain our action segmentation module to only look for actions associated with the predicted task. This decreases the inference time by 80 to 90% for two of the baseline models we use on two different datasets. Our improvements are not only limited to the inference time, but also we show that the baseline results also improve on both datasets upon using this top-down paradigm. We also offer at the last row a CDF-L result where we provide it with the ground truth task predictions, or the ground truth labels. We also show that not only we were able to establish state-of-the-art in action segmentation, but also we were able to achieve state-of-the-art in task classification using our two-stream network, where we beat state-of-the-art. Thank you very much.